So today we're talking about molecular mechanisms of action for neuropsychiatric drugs. And we're going to notice that there's only 19 slides today, but it's still going to take close to an hour. It's 19 slides because I wrote this from scratch, and this is what my presentations actually look like, as opposed to the ones that were handed to me that I have edited, but not completely smooshed and made my own. So the most important thing about understanding the mechanisms of action for psychiatric drugs is to go back and review our basic neuroscience. So we're going to go way back to basics. There's not too much about details of the action potential today. We don't really have to take into consideration as much the calcium, the sodium, the potassium. It plays a role, absolutely, especially in drugs that have side effects in the nervous system. But today we just need to remember that there is a series of action potentials that propagate down that axon. So we're going to have circuits today. We're going to care a lot about circuits. We're going to have a neuron synapsing onto another neuron, and that neuron is going to propagate action potentials, and those action potentials are going to cause the release of neurotransmitters into a synapse, which is a space. And that neurotransmitter is going to cross that space, and it's going to bind to receptors on the next neuron in a circuit. We're going to care a lot about that synapse today. So just to give you a key and a little bit of a preview of some of the neurotransmitters that we're going to be messing with today with all of our drugs. In the literature, if you look up serotonin, you are going to see this annotation for serotonin. 5-HT literally stands for 5-hydroxytryptophan, which is really easy to say. And it is a metabolic precursor for serotonin, but for some reason in the documentation, in the literature, 5-HT is the preferred abbreviation for serotonin. Sometimes I abbreviate it SE, capital S, capital E. But more often you will see 5-HT. So today, when you see 5-HT on a slide, that means serotonin. Dopamine, we're going to say, is DA. We're going to use dopamine for pleasure pathway, learning pathway, and motor pathways. And we've talked about this a lot in the past. Do you guys remember what that motor pathway is for dopamine? Nope, just quiet. Motor pathways for dopamine. What are those things called that give you Parkinson's? Basal ganglia, there we go. All right, norepinephrine. You've heard of norepinephrine as both a neurotransmitter and as a hormone at this point. Today we're talking about norepinephrine, the neurotransmitter, and it has roles in wakefulness and mood. Having more norepinephrine helps you stay awake, and it actually does modulate your mood. GABA and glutamate are actually our most common neurotransmitters. Glutamate's the most common, GABA is the second most common. So really all of these pathways are eventually going to go to something that's either GABA-ergic or glutaminergic. It's either going to suppress, depress, and by depressant we don't mean sadness. By depressant we mean inhibition. We mean less excitation of something downstream. And glutamate is the opposite of GABA. It is going to be the main excitatory neurotransmitter. It's going to increase the activity of downstream neurons. Now I'm going to show you this pathway for a couple of reasons. This is the dopamine rewards pathway. I'm going to use this as an example pathway because we have to take total circuits into consideration. Now, I'm also showing you specifically the dopamine rewards pathway because this way you can have a more intelligent conversation about addiction than you would be able to otherwise if you didn't know this pathway. So I'm going to work a little bit backwards. Basically our circuit for pleasure is that we have this ventral tegmental area, or VTA, and that projects onto neurons in the nucleus accumbens, and that nucleus accumbens projects into the prefrontal cortex. VTA is going to release dopamine. We actually already know this. Believe it or not, you actually know this already. You just know it by a different name. It's the substantia nigra of the midbrain. You guys remember that? Yeah, that black stuff. That black stuff is the metabolic waste of producing dopamine. And you've seen that before. You've seen that projecting to the basal ganglia. So what this picture is showing you is one of the nuclei of the basal ganglia. It's known as the caudate. And here's the nucleus accumbens right here in yellow. It's where that marker is right there. There's the nucleus accumbens. So the nucleus accumbens and the basal ganglia are very connected to each other, and they're very close together. So it's not a mistake that the pleasure pathway is right next to the motor pathway. It's because that's where the dopamine is going. The other concept that's important here is disinhibition. Ultimately, this is a pathway of disinhibition. It means that dopamine from the ventral tegmental area actually lands on dopamine receptors that inhibit the neurons of the nucleus accumbens. And again, those nucleus accumbens neurons are GABA-ergic. So what we have is inhibition of an inhibitory pathway. Did that make sense to you guys? I may be speaking kind of robotically for the mic, so please tell me. Does anybody want to kind of rephrase that to confirm that we got it?
Inhibition of an inhibitory pathway?
Yeah.
So it allows things through.
Yeah, so it's going, if this is the GABA-ergic neuron that's going to suppress everything, this neuron is going to suppress this neuron so that it can't suppress things. Yeah, I know. That's why we're going through it. Disinhibition is an important quality today to our psychopharmaceuticals. Yes?
So does it work more, I mean, not directly, but work more as a glutamate agonist?
So specifically, it's going to decrease GABA, but it's not exactly a GABA-ergic antagonist either. It's just inhibiting the GABA-ergic neuron. It's not blocking neurotransmission. It's just making it not happen in the first place. So we're going to have all these different drug classes and names, and they are literally going to be translations of what it's doing, and that's the good news for this, right? So this is specifically a disinhibition, but it's not a glutamate agonist, and it's not a GABA antagonist necessarily, not directly anyway. Maybe an indirect GABA antagonist, but not blocking anything. So that's cool, right? So I've even heard this in like memes and on t-shirts. Technically serotonin and dopamine are the only things you've ever enjoyed. Has anybody ever seen that one? That's totally wrong. Technically glutamate and GABA are the only things you've ever enjoyed, because this is all just about glutamate and GABA at the end. Fun, right? Yay. So let's get into some specifics. Interestingly, fun side note, and it may be interesting to take note that my notes in this PowerPoint are full of links to interesting things, especially citations for specific resources. For benzos, we've had these basically from the 70s and 80s and on. Most of the academic papers are from the 70s and 80s. It's like we figured out benzos back then and we really haven't revisited them since, is the feeling I get about benzodiazepines. For benzos, we're going to look right down to that receptor. This is a receptor located in the postsynaptic neuron of the synapse. And it's going to be affecting a GABA receptor. It's an allosteric agonist, which means it doesn't directly make you have more GABA or anything like that. It increases the affinity of GABA to GABA receptors. So the same amount of GABA is going to bind to this receptor more often, more times, more frequently. So your GABA activity will increase. So we'll give this to people with anxiety on the basis that they have some overactive neurons. They have too much activity in certain brain regions, and we're going to suppress some of that activity, and it's going to make them feel calmer. That's the idea. So GABA doesn't necessarily make you feel bad. It's not necessarily, it is literally depressant. It's not making you feel sad. Sometimes you feel really good when you have elevated GABA. With all these neurotransmitters, it's just about where they're going and what they're doing. So benzos are allosteric agonists. Our next group is tricyclic antidepressants. Again, this name is a little bit older. We've had these a little bit longer. What we're going to find is that it's a reuptake inhibitor. So let's look at that synapse one more time, because we're going to see a lot of reuptake inhibitors. We have to talk about clearance of neurotransmitters from the synapse. We have neurotransmitters in the synapse, and they have to leave eventually. If they don't leave eventually, we are going to continue to have downstream activation over and over again. So they can simply diffuse away. Or another mechanism allows us to recycle neurotransmitters via reuptake transporters. We're going to have specific proteins on the plasma membrane that allow us to bring that neurotransmitter back up into the presynaptic neuron, that synaptic terminal. And then it can be repackaged into a vesicle and used as a neurotransmitter again. So reuptake in and of itself is not a bad thing, but hypothetically, if we block that transporter, the way my cursor is blocking this transporter right here, then that neurotransmitter will stay in that synaptic cleft for a little bit longer. That's the idea with reuptake inhibitors. So our tricyclic antidepressants are going to inhibit the reuptake of both serotonin and norepinephrine, as in the neurotransmitter norepinephrine, not hormone. Yes?
So by blocking the receptor, the reuptake transporter, it stays there longer, which means it can take more up?
Not that it can take more up. So her question was, by blocking this transporter, it stays there longer, allowing for what precisely? Allowing for this neurotransmitter to keep diffusing over to the postsynaptic neuron, adhering to the receptors on that downstream neuron over and over again to increase, most likely, excitation, because this is serotonin and norepinephrine. So to increase excitation of the downstream neuron is what that's allowing for. Good question, thank you. Any other questions about that before I move on? You're going to see another drug class that specifically inhibits reuptake of serotonin and norepinephrine. Tricyclic antidepressants may have other long-term effects. Changes to these receptors right here is what is suspected. Unfortunately, even though we've had tricyclics for a very long time, we do not understand what that mechanism is or what it is specifically. Wah, wah. So I mentioned you're going to have reuptake inhibitors that are selective to serotonin and norepinephrine, again. So we'll also call that drug class SNRI. This will be considered a different drug class, even though they are mostly doing the same thing. SSRIs are selective serotonin reuptake inhibitors, which means what? What do you think that means? Yeah, so it's just specific to serotonin. It does not block the norepinephrine transporters. So there it is, drug class, drug name, boom. At this point out, it's just that. It's just drug class, drug name, all the way through. Tells you what it does. MAOIs, that means that we are inhibiting the enzyme monoamine oxidase. Here's our monoamine oxidase protein. It's going to break down serotonin, dopamine, norepinephrine, and epinephrine. So if we can stick a little wedge in this guy's mouth, chemically speaking, and he can't break down those neurotransmitters, you should have elevated levels of all four of those. Pretty clear, right? Any questions about that one? Cool. Atypical antidepressants, we think, are going to act a little bit differently, and they're going to be heterogeneous, which means they're going to be very diverse. There isn't going to be one mechanism of action for atypical antidepressants. But the chemicals that atypical antidepressants will affect will be dopamine, serotonin, and norepinephrine. There's at least one type that is going to be a serotonin antagonist, which seems really counterintuitive. But by shutting down serotonin, your brain may have a compensatory mechanism where it increases norepinephrine. And we talked about earlier in patho how, you know, there might actually be more than one neurological disease that correlates to depression, lots of different forms chemically of depression. Maybe somebody's form of depression is actually low norepinephrine. We don't really test those levels before we start administering drugs, so we don't know who we're giving what drug to right now, or why we're doing it. So if we can increase the efficacy of norepinephrine, that may actually help very specific people. Okay, that was antidepressants. Any question before I go to mood stabilizers and antiepileptics? Is this helping so far? Good. Lithium's a weird one because it is elemental lithium. In my imagination, this is probably not reality, but in my brain, some geologist somewhere who had a mood disorder licked a rock and felt really good afterwards, and that's how we got this drug. It's going to modulate GABA, glutamate, and dopamine. Even though this is one of our oldest psychiatric drugs, our mechanism of action is unknown. There are some newer MRI studies that suggest it's neuroprotective and neuroproliferative, which means you're going to have a more robust neocortex. You're going to have thicker cortical gray matter if you're on this for a long time. So that's good. It's neuroprotective. It seems to be generally good for you. Again, it's kind of a that we just throw at people because it seems to work. We don't know why. I think this slide was the hardest for me to write. First of all, because I knew the least about it, and I don't think this was even much of a thing when I was taking undergrad pharmacology, or psychopharmacology, that's what I took. But here we go. Here's what I gathered after much researching and condensing. They seem to be GABA-ergic, which makes sense for both bipolar disorder, those manic episodes, and as an anti-epileptic, where we have runaway synchronicity of neurons. We want to calm those neurons down, so GABA-ergic makes sense. But it's still going to be different from our GABA-ergic hypnotics that we're going to talk about for sleep disorders in some ways, so it's not 100% that. Anti-glutaminergic, it's going to inhibit glutamate release in some way, thereby decreasing excitation. Suppression of various excitatory amino acids. Yeah, I don't know. VPA increases turnover of dopamine, but we don't know if that's part of its mechanism of action or not. Hooray. And we seem to see increased serotonin levels in people who are taking anti-epileptic drugs, but we don't know why. So, gigantic question mark on this one. Here's a random fMRI. I couldn't find comparison fMRIs for epilepsy versus bipolar disorder. I tried. None of them look very impressive, is what that's about. If you have, even if it's epilepsy, you could have very focal epilepsy that's just causing a blip in your fMRI in one small area, and it's going to look a lot less impressive than this picture that I chose for you. But that's the general idea for both of these, is overexcitation. Okay, questions about that before I move on to the dopaminergic pathways? We're about to go into antipsychotics, and in order to talk about antipsychotics, we need to talk about dopamine, and in order to talk about dopaminergic pathways, we have to talk about D1 receptors and D2 receptors. And I think what I have written here contradicts what I said in patho earlier. Yep, it does. That's okay. We'll deal with it. I don't think you'll ever have to memorize these pathways for the basal ganglia. What I'm getting at is that those D1 and D2 receptors travel along different pathways, and one is excitatory and one is inhibitory. So if you just block dopamine to deal with a disorder that has overabundant dopamine, you're going to have motor side effects. So what I can give you for your conventional antipsychotics is more of an explanation of the side effects than the explanation for the primary effects. Conventional antipsychotics block D2 receptors, so they will be dopamine antagonists. They will decrease the ability of dopamine to bind to those receptors in the basal ganglia. for the D2 pathway, which according to this slide, decreases your unwanted movement. If you have disinhibition of this system, what are you going to get? It's going to allow things through, therefore you're going to get unwanted movement. And that is your side effect of your conventional antipsychotics that block D2 receptors. You're going to have extrapyramidal symptoms, there should be an A there, such as tardive dyskinesia. It's not the only one, but it's a lot of them. So I always say that Parkinson's and schizophrenia are two sides of the same coin. There is actually a state in Parkinson's treatment where you can have overactive dopamine and enter a state close to psychosis. And there is treatment in schizophrenia that gives you Parkinsonian symptoms. As you elevate dopamine too far this way, you get psychosis. As you decrease dopamine too far that way, you get movement disorders. That's the takeaway there. Fine, right? It's an interesting one. Atypical antipsychotics still block the T2 receptor, but they have a shorter association time, so it's going to be a little bit more modulated than our classic antipsychotics. They're also going to be serotonin antagonists, specifically to the 5-HT2A receptor. This is part of why I need you to recognize that 5-HT as our annotation for serotonin. And I think I've mentioned this in your courses before. There are at least 19 different subreceptors for serotonin, and they all do different things. This one, it doesn't only do hallucinations, but with abundant serotonin, this can be a source of hallucinations. That's why there's something specific telling you about that receptor right there. This is the receptor that LSD binds to. Cool, right? And for those of you at home, there were finger guns just then. All right, any question about typical, atypical antipsychotics? And even more modern treatments for schizophrenia aim, as we mentioned in Patho today, to balance out the dopamine levels rather than simply suppress the D2 receptors.
Can you just say one more time that increase of dopamine and that decrease?
Increase dopamine to decrease.
I can't remember.
Oh, yeah.
Part.
Blocking D2 receptors is going to have the effect of disinhibition. It's going to create more unwanted movement because that pathway is about decreasing unwanted movement. And I'll double check that for my Patho slides. Again, I don't think I have any test questions about D1, D2 in Patho. I think it's an important concept overall because it ties into this. But I'll check it, check my own understanding. It's really easy to mix those up. Onward to amphetamines. We talked about this conversationally in Patho a little bit today. Hold on just a second. What are our catecholamines again? Epinephrine, norepinephrine are catecholamines, absolutely. So amphetamines are going to increase your catecholaminanergic, as in catecholamines, as in epinephrine, norepinephrine, probably mostly norepinephrine, because it's right there. And that's going to make it a CNS stimulant. Here's our specific nucleus that's releasing norepinephrine. This is a slide that I borrowed from my sleep lecture. Isn't it beautiful? These are part of your circuits that keep your brain awake, which is why that's a relevant statement to make. The fact that I took this from the wakefulness part of my sleep lecture tells you a little bit about what that pathway is doing. Methylphenidate for ADHD and narcolepsy, reuptake inhibitor for norepinephrine and dopamine in the prefrontal cortex, which again regionally is up here. Prefrontal being considered to be more the site of morality, efforts, conscious thought, decision making, not being a jerk to people, things like that. And me saying not being a jerk to people is not a mistake. If you're wondering why, look up Phineas Gage if you have not done so already. But ADHD does not just have amphetamines. You could also attempt to use antidepressants that we've already discovered. Norepinephrine reuptake inhibitors are an option. Antihypertensives. Yeah, that's about it. I don't have anything extra for you there. Any questions? It's kind of a shot in the dark for a lot of ADHD treatments that are alternative. Okay, GABA-ergic hypnotics, yay! So the examples of GABA-ergic hypnotics are going to be your things like Ambien, Lunesta, things like that, the commercial names. So just from what it says, what do you think it's going to do? Make you sleep. And here's another slide I took from my sleep lecture. So it's going to affect this GABA-ergic pathway right here. It's going to increase the activity of this guy, the VLPO. You don't need to know what the VLPO is specifically. It's fun neuroscience if you're interested. I'll let you in on it. It's just going to be a GABA receptor agonist. It's going to help GABA binds to GABA receptors, which can be great for making you sleep because if you notice, look at all of these yellow dots, and then look at all of these yellow dots. Notice anything interesting about those yellow dots? They're the same yellow dots. So here's your wakefulness pathways, and here they are being inhibited by GABA. Cool, right? So now we're just inhibiting all of our wakefulness pathways. Yes?
Why are the side effects of these drugs sleepwalking?
Good question. So GABA may be increasing in other brain regions that are not necessarily inhibiting just the sleep pathway. That might be something I can better answer by pulling out my sleep lecture afterwards. Let's do that instead. But yes, as she's getting at, GABA-ergic hypnotics have a lot of really undesirable side effects such as sleepwalking, sleep eating, forgetfulness. I know I was having a lot of forgetfulness when I was on Ambien. It was like tabula rasa. I would tell people towards the end of my usage of those that, you know, whatever conversation you're having with me tonight, I might not remember it tomorrow. And that has some really nefarious uses now. Some people use it as a date rape drug because your memory is so unreliable that you can't go to court over it. So that's really bad. Therefore, we need another treatment or another pharmacological intervention for sleep disorders. And the Orexinergic pathway is a slightly more recent discovery. At least I've only started seeing it advertised very recently, which I think is awesome. We found out about the Orexinergic pathway because of narcoleptic puggies. Yes, that is what's happening there. That's a narcoleptic puppy. They interbred/inbred dogs with narcolepsy to find out what was neurologically different about them. And what they found was neurologically different is that they were lacking orexinergic neurons. So orexin is also known as hypocretin, and it helps keep you awake. And if you are narcoleptic, there's a good chance that you lack these neurons for some reason. Therefore, we can use orexin receptor antagonists to block the effects of orexin, and then you get to fall asleep, basically. Or at least what it really is mimicking the states of narcolepsy, which a sleep attack is not really sleep. Is anybody familiar with narcolepsy and sleep attacks? You want to talk about sleep attacks for a second?
I mean, what do you mean?
Anything about them? Any, like, what the experience of a sleep attack is?
I mean, I've only had one when I thought I had it, but it was more like hallucination almost, but
Okay.
I did fall asleep right.
Okay.
And then I had like a very vivid lifelike dream.
Okay. Yeah, so there's a variable experience for people with diagnosed narcolepsy, I should say, where a sleep attack isn't necessarily unconsciousness. A sleep attack is going to be suppression of motor pathways and a state very close and similar to sleep, but a person could be fully conscious while experiencing a sleep attack and conscious of the world around them to some extent. So it's not really sleep. So some people who get on orexin receptor antagonists sleep like a baby. Some of them lie there paralyzed for 9 hours and completely powerless to do anything about it. And it's kind of nightmarish, and that's the anecdotal thing that I've heard about it. Hooray. We can also use orexin agonists to treat narcolepsy and prevent sleep attacks. That's the end of the slideshow. If you want, we can talk about caffeine and how caffeine works real quick, because I always like to do that one. Okay. And it's not going to show up there. That's obnoxious. I'm going to draw it on my board, but I'm going to put it on the screencast. So adenosine. It's not going to work at all. You know what? Let's just make this auditory. All right. You have adenosine in your body. What do you know about adenosine already? It is part of ATP. Yes, adenosine plus 3 phosphate groups equals ATP. If your adenosine is free and not bound up in ATP, that is a sign that your cells are tired. They are fatigued. Your mitochondria cannot produce more ATP right now. So you're actually going to have cells with receptors for adenosine, just adenosine. Adenosine is going to bind to an adenosine receptor, and that's going to send a signal to your central nervous system that says, I am tired. And that is why you feel tired throughout the day, is because you have more free adenosine. Caffeine is an adenosine receptor antagonist. It blocks the receptor for adenosine. So the adenosine is still there floating around. It just can't bind to the receptors. So your body can't gather that information that your cells are fatigued. Therefore, you do not initiate the behaviors related to fatigue. Cool, right?
If that's the case, can your body make more ATP if it's blocking it from entering?
I don't think the caffeine changes your adenosine level. What is going to happen is eventually the caffeine binding to that receptor is going to go away, diffuse away, and then you're going to have a higher buildup of adenosine because you waited a lot longer to intervene in your tiredness.
Oh, so that's the caffeine crash.
That's the caffeine crash, yes. So it doesn't really necessarily change it. The only ways to get your adenosine levels back down is to make it so that your cells can produce more ATP by getting sleep or food or both. That's it. It's your only option. Cool, right? All right. Thus concludeth the lecture. That was really short.